So, hi everybody, I'm virtual Bruno Escoffier in the corner here, and I will talk today about a joint work with Euripides Bampis. So we're both from Sorbonne University in Paris and Alexander Kononov from Sobolev Institute of Mathematics about LP-based methods for multi-stage minimization problems. So as an introduction, I will talk about the framework of multi-stage optimization. And then, of course, talk about the results we obtain. So multi-stage optimization is a framework that aims to consider problems, optimization problems where some data are able to evolve with time, okay? So some weights in your graph, some prices, some demands that are not constant over time that can evolve. And the goal in this framework is to maintain the feasible solution, hopefully a good feasible solution over time, over the whole time horizon. And this implies some modification, of course. If the price of a product gets high, then we may want to change product at some point. And in the framework, we consider that it's costly to move from one solution to another one. So we have transition costs associated to the modification we make in the solution. Okay, so this idea has led to a model introduced in two ICAL paper in ICAL 14, so that I know details. So we have discrete horizon time of, let's say, capital T days, so 1, 2, up to 2t. And for each of these days, we have a specific instance of our problem. Okay, so we may have specific weight function, WT, or even set of feasible solution, a capital F here. And so a specific instance of our problem, and the goal is to find a sequence of feasible solution, okay, one for each day, S1 up to ST. To this sequence of solutions are associated two quantities. So the first one is what is usually called the service cost. So service cost is just the sum of the cost of solution. So S1 cost me W1 of S1 for day 1, and the same up to day T. So my service cost is just the sum of the value of my solutions. But as I said earlier, we also consider transition costs. So we have a function delta that maps to a value, a negative value, a pair of solutions. Okay, so delta of st minus 1 st is the cost of moving from solution st minus 1 to solution st. You can imagine, and this will be the case in the whole talk, that if a solution is a subset of vertices, edges in your graph, let's say, then you will pay something. You will have a transition cost each time you change your solution by adding or removing an element. So we can imagine that the transition cost is the size of the symmetric difference between two consecutive solutions. So number of elements that are in one solution but not in another one. And in this framework, the goal is simply to find a sequence of solutions that minimizes the sum of service cost, so cost of solution, and transition cost, moving cost. Okay, so two examples. The first one has been studied in this article of Gupta et al. And it's about the perfect matching. So as an input, you have a graph, which is fixed, okay? And you have a sequence of weights for your edges. So WT is as an edge weight at day T. And you want to find a sequence of perfect matching. So your graph admits perfect matching. So sequence M1 up to MT. The service cost is just the cost of the matchings. Okay, the WTMT is the cost of the matching at day T. And as I said earlier, we imagine that we have a transition cost, so you pay 1 or a constant C, whatever, each time you change an edge or you remove or add an edge in your matching. Okay, so transition cost is a symmetric difference between two consecutive matchings. And we want to minimize the sum of service cost and transition cost. Another example that we will consider in this talk is multi-stage vertex cover. So it's exactly the same, but now we have a sequence of weight on vertices instead of edges. And the solution, we only sequence of vertex covers instead of matchings. Service cost is the cost of the covers, and now we also pay 1 each time we add or we remove a vertex from a solution cover. Okay. So as I said earlier, there has been the perfect matching maintenance problem has been studied in Gupta et al, and we have some negative results for this, even if the so-called offline case. So just to be clear, offline means that I know the whole data, the whole set of instances when I have to solve the problem. So and we can also imagine an online setting where I discover the instance of day t, and I have to choose my solution st without knowing the data for the future. But this is not the case, and this won't be the case in this talk. So we stick with the offline case. I have a perfect knowledge on the set of instances. And even in this case, perfect matching maintenance is not, so it has not a constant approximation algorithm unless p equals np, and either for 2 time steps. Okay, so you have a graph, 2 set of weights, and you want to compute 2 perfect matchings that are both of small weights and that are not too far from each other. Not possible to get constant approximation algorithm. And so in this talk, we were interested in considering other multi-stage problems and maybe getting approximation algorithm using LP-based methods. And this is basically the topic of the work. Okay, so end of introduction. And now we will talk about 2 problems in this talk. So the first one, so 2 problems, both on graphs. The graph is fixed, and we have some weights, either on vertices or edges, and the weights change over time. And okay, so we'll talk about the multi-stage vertex cover that I defined slides before, and also another problem which is called price collecting Steiner tree, and I will define it later when I talk about it. Okay, so let's first focus on multi-stage vertex cover. Okay, so let me just remind you a very simple algorithm for the classical vertex cover. So we just write an integer linear program with a variable xi, which is 1 when you take the vertex and 0 otherwise. So you have some constraints ensuring that you cover edges. You want to minimize the value of your solution, the weight of your solution. And a very simple algorithm, you solve the continuous relaxation, you get a fractional solution x star, and you round it as follows. You take the vertex if and only if the continuous variable is at least 1/2. Okay, and this is a very well-known 2 approximation algorithm. So can we do the same thing for our multi-stage vertex cover? Well, let's try to write an ILP first. Well, now we have variable xit, which is 1 when I choose vertex vi at time t. So I have the same set of constraints. Cost is similar for the cost of covers, but now I have transition cost. So recall that it's 1, I have a transition cost 1 if I take one vertex at time t and not at time t minus 1 or vice versa. So basically the cost is just the absolute value of the difference between the consecutive variables. Okay, so if they are the same, 0. If it's 0, 1, then the cost is 1. So I can write the transition cost this way, and it's easy to linearize using new variables. So I can write an ILP quite easily. But remember that the cost is of this form. Okay, now I can solve it and use the same running, so the continuous relaxation, and use the same running scheme. So let's try to analyze this very simple algorithm. Of course, it is a feasible solution because of the rounding, no problem. For the service cost, for cost of covers, and it's also okay, I have a ratio 2 for the very same reason as for the classical vertex cover, because of the rounding. I have the rounded variable, which is at most twice the value of the continuous one. Okay, what about the transition cost? There I may have a problem. Why? Because imagine that for vertex, I have these two consecutive values for t minus 1 and t. So one is 1/2 minus epsilon and the other one is 1/2 plus epsilon. Why is this a problem? Because when I round, this will be rounded to 0, this will be rounded to 1. Okay, so if I look at the transition cost, the difference between consecutive variables, then for the continuous value, it's 2 epsilon, very small. And for the rounded value, it's 1. And so the ratio is unbounded. Okay, so if I have this situation, then I have unbounded ratio. Well, actually, this will not happen for vertex cover. And let me explain why briefly. For vertex cover, for the classical vertex cover problem, we have the semi-integrality property. It says that if you consider a basic solution of the LP, the continuous relaxation, then each variable will be either 0, 1, or 1/2. Okay, cannot be something in between. And actually, it turns out that for the multistage version, it's the same. Okay, we can show that it's also true. So each variable x star it will be either 0, 1, or 1/2 in a basic solution. And this solves the problem because this cannot happen there. Okay, it's either 0, 1/2, or 1. So when I round, I have a transition cost when I round. To get a transition cost when I round, it means that the two continuous variables were not equal, and so there was a gap of at least 1/2 between them. So now, when I get a transition cost in my rounded solution, I had at least 1/2 in the continuous solution, so I also get ratio 2. So this means that the very simple rounding gives a two approximation algorithm for vertex cover. So this is simple, but remember that for the perfect matching case, we had the impossibility to get constant approximation algorithm. Okay, so let's now get to the bit harder case of price collecting Steiner tree. We'll first introduce a problem. So I guess you all know Steiner tree problem. So we have a graph G. You have edges, weight on edges. I will present it with a root R and a set of so-called terminals, so capital R. And the goal is to choose some edges to connect the vertices in R, all the vertices in R. Let's say there are clients, so we have to serve all the clients in R by connecting them to the root R. We can go through some other vertices, but it's not mandatory to connect the other ones. A well-known NP-hard problem. And there is also well-known generalization called price collecting Steiner tree, where now you have the same instance, but you don't have to connect everyone. You can choose a subset S of vertices that you will connect through some edges to the root. Okay, so you pay these edges to connect the chosen set of clients S. But you have some clients that are you choose not to connect to R, and for them you will pay a penalty. Okay, so you have a penalty associated with each client, and if it's not connected, not served, then you pay a penalty. So if the penalty is very high, then you have to connect them, and you get a Steiner problem. Okay. So we consider a multistage version of this problem here. So as previously, the graph R, capital R fixed. And what evolves is the edge cost and the penalty cost. So each time t, we have a penalty cost pt and an edge weight wt. And we have to choose for each time step, for each day, the set of clients that we will serve, okay, and of course, edges to connect them to the root. What is the transition cost? Where we imagine that clients matter, so we will pay a penalty, we pay a cost, a transition cost, when we change our decision about serving or not a client. Okay, so the transition cost is the size of the symmetric difference between two consecutive set of served clients. Okay, and now, as previously, I have to minimize the sum of the service cost is now edge cost plus penalties, and I have this transition cost about served and unserved clients in consecutive solution. So I have three terms in my objective function. Okay, so what can we do? Well, let's try to mimic the previous idea and use ILP and rounding. So we write an ILP. So now we have a variable SIT, so which is 1 if I choose to serve client ST at time t, and 0 otherwise. We also have variables for choosing edges for connecting the clients. And the transition cost, so it's about serving the clients, and as previously, you can write it as the sum of the absolute value of the difference between consecutive variables. And we can linearize it as well. So we can write this ILP, solve it. Now we have to be careful with the feasibility of solution. So what we do is we will use a rounding scheme to decide for each day the set of clients we will serve. So based on these values, S star. And once we have fixed the set of clients, we will solve a Steiner tree independently on each day to choose edges. Okay, so one crucial point is this rounding scheme, because we have to get a rounding scheme that avoids unbounded ratio for transition cost. Remember that we got in the previous slide. So for this, we divide a new rounding scheme that I represent now, and then I will briefly show how this rounding scheme allows to get approximation algorithm for this problem. So let's consider a variable or a client, and this is the evolution with t of the values, let's say SIT for some SI. So in the two threshold rounding scheme, which was two threshold alpha and beta, and we round using three rules. In the first one, it says that if my continuous variable is very low, so below beta, then I round it to 0. Second rule, if it's at least alpha, then I round it to 1. Okay. And then I have to decide what happens for the variables between alpha and beta. For this, I look at this group of variables, and so for this group, both on the left and on the right, variables were rounded to 1, okay? So I round them to 1. And in all the other cases, I round them to 0, okay? If they are adjacent to some variables that have been rounded to 0, then I round them to 0. Okay, and this is the two threshold rounding scheme. And actually so there are three rules, and there were three terms in our function to be minimized, and each rule we served as to bound the error made in each of the three terms. So let me briefly explain why. So the first rule basically says that I round to 0 if the variable is not too high, and this basically allows to get a bound on the value of the variables SI, and basically it says that hat of SI is not too high, so I won't have to pay too much to connect the served client to the root, okay, because this value is not too high. And if I use not any but a proper two approximation algorithm for Steiner tree, I can have this ratio 2 times what I lose when rounding, so this ratio 1 over 1 minus beta, okay. So the first rule allows to bound the ratio on edge cost. The second rule symmetrically allows to bound 1 minus SI, okay, with a ratio 1 over 1 minus alpha, and this allows to bound penalty cost, because this penalty cost is PI times 1 minus SI. So if I have this bound, I immediately get a ratio 1/1 minus alpha for penalty cost. So rule 2 allows to bound penalty cost, and the trick is on rule 3. And this rule allows to get bounded transition cost. Why? Because if I look at the transition cost in my rounded variables, so for instance, this one, it was 1 and it goes down to 0. It is because, I'm sure that there were, in the continuous solution, one variable above alpha and one variable above beta, okay? So if I get a transition cost of 1, it was because in my continuous solution, I had a transition cost of alpha minus beta at least. So I lose a factor at most 1 over alpha minus beta for transition cost. So it's bounded. And now I just have to play with alpha and beta, and with this value, I get a ratio 4 for all the 3 costs. And so I get a 4 approximation algorithm using these two threshold bounding scheme. Okay, so it was maybe a bit fast, but I hope the idea is clear. And so for the last slide, so we can improve this last result using a trick on the thresholds. So we get 3.53 approximation algorithm for Steiner tree, price going Steiner tree. We also have other results. For instance, multistage min cut is polytime solvable. Okay, another result for another price collecting problem. And basically, so I would like to emphasize the result, saying that we at least partially answer the question. LP-based methods are indeed useful to get approximation algorithm for the multi-stage problems we consider. And to achieve this, we introduced a new rounding scheme, which is interesting because it fits this multi-stage framework and it allows to bound the transition cost. Okay, so this is an interesting part, I hope. So one direction would be to focus on the online case. So when we have no information or few information in the future, to see if LP-based method can also be used in this case to get interesting approximation algorithm. And also to conclude the model, so there has been several works in the last few years on this multi-stage optimization in the model I present, but also in the other case where you put some bound on the number of modifications that you are allowed to do, and this gives to interesting parameterized problems. So there have been some work in parameterized complexity. So you have here natural parameters, the number of modification you make or the size of your solution you get. And so for vertex cover, for instance, and other problems, there have been some parameterized complexity works as well. And that's all. I hope that you're interested in this kind of models. And thanks for your attention, and have a nice virtual WAOA conference.